This video will address several things that you have to be able to tell from functions and the graphs of those functions. One of those is the idea of increasing and decreasing. Before we look at the fancy definition, just think about the words increasing and decreasing. Think about this kind of like a roller coaster. Isn't this from all the way to here, all the way up, isn't that increasing? And when it reaches the top there, when it turns around, it's going to begin its descent, and it's going to be decreasing all the way down here till it gets to its absolute bottom, and then it goes back to increasing. So your intuitive thought about increasing and decreasing is exactly what it says. If it's going up, it's increasing. Going down, it's decreasing. The fancy definition applies this way. This says, if x sub 1 is less than x sub 2. So let's take a look at this over here. Let's take this point compared to, let's say, this point. That point right there is the ordered pair -2, 0. That ordered pair right there looks like it's about negative 1.8-ish, and the y value is 2. So take a look at this x value, that's my x sub 1. Is -2 less than -1.8? Yes. Take a look at the corresponding y values. The y value that goes with this -2 is 0. The y value that goes with -1.8 is 2. Is 0 less than 2? Yeah, that's exactly what this definition says. So don't let the definition bother you. It still is the idea of increasing is going up, decreasing is going down. Let's look at how this definition applies for the decreasing and show you the same idea. Let's take 2 points. Let's take this point right here, which is the point 0, 0. And pick another one along this little green area, which looks about right here, which looks like it's 0.5, -2. So let's look at the definition. Let's say this is my x1, this is my x2. So is 0 less than 0.5? Yes. Let's write the corresponding y values down. The y value that goes with 0 is 0. The y value that goes with this 0.5 is -2. But 0 is greater than -2, which is exactly what the definition says. Another thing to point out here is that these are open intervals. That means when we get ready to write these on the next page, they will be the curved parenthesis. And the reason is this. The open interval means the point you write down is not included. When you think about this point right here, which is where it is turning from increasing to decreasing, that actual point where it makes its turnaround is neither increasing nor decreasing, and that's why it has to be the curved parenthesis. So when you're asked to name an increasing or decreasing interval, you need to name it with the curved parentheses. Now there is something that can happen on a function is the function can remain constant for a particular interval. If you just look at this, this looks like we're decreasing to here, and then we remain constant for a while, and then we decrease again. So the function doesn't have any increasing intervals, and that's okay. You don't have to have all of them. So let's take a look at a couple of examples and name these intervals. We want to name the intervals over which the function is increasing, decreasing, or constant. So I like to look at one type all at once. So increasing, where's it increasing? All of this is increasing. So let's just deal with that little green part. Our interval is increasing from here to here. Remember, you are looking at the x values and you name the interval. It's going in that direction with the height, but we are naming the x values. So it's increasing from the origin, which is 0, over to here, which is the 0.2. We are counting by 0.5 units, so that is the 0.2. That's the only place on our graph we are increasing. There are 2 places that we are decreasing. This is decreasing all the way in from the far left, which is -infinity. I keep emphasizing the fact that when you are naming these intervals, you are naming the x values. Don't think this goes on and on and on, y value into positive infinity land. We're talking x. It's getting bigger and bigger going out this way, which is a -infinity for the x. Where does it reach its bottom point? Right here, where we've already said it's turning around to increase. So we've got that same 0. We had to begin that interval. Same idea over here. Here was the end of our increasing right here. It turned around at this peak, so it is beginning to come back down again. So it begins at 2, and it goes off to positive infinity. Anytime the graph has got arrows on it like this, then your beginning of an interval will be negative infinity, and an end of a different interval will be positive infinity. Is there any place in here it's constant? No. All right, let's take a look at increasing. This is increasing actually in two different intervals. It's increasing from all of here to here and from here. So along this interval, there are implied arrows. The reason there's no arrows drawn on the paper is because this is like a screen clipping from your graphing calculator. So the arrows don't show up on your graphing calculator. I just point that out so that when you do these looking at graphing calculator graphs, you won't think the graph ends. The graph only ends because your screen is only so large. These are continuous functions. They continue going. So this increases from way over here, which is our negative infinity, until it reaches its peak right here, which is -1. It's also going to increase here all the way up. The x value that corresponds to that ordered pair is 1, and it continues all the way out to the right, which is positive infinity. There was a decreasing interval along this little path, so it had to stop increasing here where it turned around. So that's that same -1 that ended that interval, begins this decreasing interval. And we get to here where it turned around and began increasing again, so we're going to take that x value, which is 1. And this one also has no place where anything remained constant. Now I purposely drew this one without arrows because I don't want you to think every interval has to involve infinity. This began right here, no arrow, that began right here, and it continued up to here in an increasing fashion. So our increasing interval will be from 0 to 2. Then it runs constant for a while. It runs constant from 2 over to 4. At that point, it begins increasing again. So from 4 over to 6, it increased. There is no place on this graph that it decreased, so we'll just put none for the decrease. All right, here we go again with a fancy definition that is pretty intuitive just looking at the term. A relative maxima and relative minima. Think about what the word max refers to as maximum, and minima refers to minimum. So, fancy definition is a function value f of a is called a relative maximum of f if there exists an open interval containing a such that f of a is greater than f of x for all x not equal to a in the open interval. In basic plain English, f of a is called a relative or sometimes called a local maximum if f of a is greater than all other values of f near a. You can think of it being the highest point, kind of in the neighborhood. So take a look at this. F has a relative max right here at -1, 2. It's reached a peak right here. This does fit this definition from the standpoint of 2 is the highest y value in the land. I mean, you can just look at your graph and see that it's the highest, just in this region. We're not talking way over here where it continues off to infinity. So f has a relative max at -1, and the maximum is called 2. There's two different things you're being asked. Where does it occur is the x value. What is the maximum value is the y value. Similar definition, a function value f of b is called a relative minimum of f if there exists an open interval containing b such that f of b is less than f of x for all x not equal to b in the open interval. Same idea as the last screen. It is considered a relative or local minimum if f of b, that's the y value, is less than all other values of f near b. Well, isn't this the lowest y value around? Yeah, that's where it reached its bottom. So that right there is considered our relative minimum. It occurs at 1 and its value is -2. So let's look at an example. Here's a little curve I've drawn out. The number at which f has a relative minimum. That means we're asking for the x value. When your book asks what is the number at which f has a relative minimum, they want to know the x value. Well, your relative minimum is occurring right here. What is the x value right there? Well, first off, the ordered pair is 2, -2. So the x value is 2. When it asks what is that minimum, that is your y value, -2. We're looking for now the number at which f has a relative maximum. Is there any place around here where we've kind of reached a peak? Yeah, actually there's 2 relative maxes, because for this neighborhood, that's the highest. for this neighborhood, that's the highest. So we're going to have to name 2 of them. That's the ordered pair 0, 2. So the number at which f has a relative maximum is 0, and the relative max is 2. The other one, this is the point 1, 2, 3, 4, 5, 1. So this one is 5, and its value is 1.